Okay, so today we are learning about containers, which most of you probably know as Docker, which are not actually Docker in all cases. Okay, so a quick clarification. Docker is a company and they make a product called Docker. Docker is an implementation of what's called OCI, which is the Open Container Initiative spec. And there are like many different implementations of this. There's like one called Podman, there are like other ones. But Docker is the most popular one. They also have a desktop client, and that's like, yeah, we use these terms interchangeably. It's like Kleenex and tissue, right? Like one of them is a like a generic item, like one of them's a specific product made by a company. So yeah. So a container is a piece of software that you package and it runs on any Linux distribution. Okay, and the implementation, right. So you have C groups, namespaces, network namespaces, PID namespaces, and like any other kind. So basically, you're isolating all of the things that like an application would need to run, but things that are not necessarily like needed, like the kernel, for example, are like not included in the container. So it's a bit like a stripped down VM that only caters to like dependencies. Okay. So here's a side by side of a VM and a container. So you can see that like each container. So like to give you a little bit more context, like if you're running like a piece of software maybe and you want to like package it like for Ubuntu because like that's what you're using it on, you might like make like an Ubuntu container that contains your piece of software, right? So you might have like a an Arch container next to like an Ubuntu container next to like a Fedora container, right? And these will all have different it'll have the application that you run, obviously, and then it'll have all the dependencies. So like I think this has been covered, but like different distributions will have like different like packaging versions, right? So if you like download a piece of software from the internet and it's like just a binary, usually you'll get an error that's like, oh, like error, like lib xyz blah blah dot so is missing, or it's like the wrong version, right? And then you'll look at what version you have, and it's like, bah, like it's like two versions ahead, and like it's not backwards compatible, right? And then you have like this version hell. So what the container does is it bundles like all the right library versions, like the right version of like CD, LS, like all these like I don't know, like glibc, right? All of that into a package, and then it bundles it with your app. So instead of running the application on your host machine, you run like Docker run and then like a container name, and it'll run it with this context. Compare that to a VM where you're basically emulating a fake machine n different times for each app with like its own OS, right? So the advantage of this is like it's much lower overhead, like much less replication, but there are also some limitations. Question?
So I guess it's a bit like Conda, I guess, with Python, but like
I don't know how Conda manages things.
Kind of, basically, it's like you have your own special environment that's sort of isolated from everything else.
yeah,
So you can add another content environment, you have all your packages isolated there.
yeah.
And
yeah,
you
or
can
like
run functions.
VMs. Yeah,
Yeah.
yeah, like that. Exactly. Yeah, that's a good analogy. Okay, yeah. It's like a VM. It's like a similar idea, but yeah. So the kernel is not bundled with each package. It's still running on your same like host machine. So like the processes are isolated, like the libraries, binaries are all isolated. But yeah, the one difference is or the important difference is that in a VM, you bring your own kernel. With a container, you just run on the kernel of the host machine. Yeah. So on Linux, this is pretty simple. You just run the Docker process and it will work on Linux because you already have a Linux kernel on your Linux machine, right? On other OSs like Windows or Mac OS, you can't. So what happens is you have to run a VM like VirtualBox, and then you have to run Docker in that. So like on Windows, for example, like if you use Windows, you may know of like the Windows subsystem for Linux. Like the Docker version for Windows will use that as a backend. So it will install like Ubuntu or whatever. I think you can configure it to use your default distro, and it'll just install Docker there. And then like it'll use that Docker installation on virtualized Linux for your containers. So yeah, I guess this is confusing. So make sure you ask questions. Okay. Yes. so here's like a comparison of the two. So yeah, with the container, you have faster startup, smaller images, low resource usage. I mean, this checks out since you're not emulating a fake machine, right? You're not bundling the kernel, and it's process isolation. You don't need to boot up an entire OS. So yeah, it is easier to package and ship. We'll get to how you do that later with Docker files. Cattle, not pets. I
Is
don't know.
Yeah. It's talking about like how all your containers are like interchangeable almost. So you can set up multiple containers or destroy them at will, and like nothing really matters because you're storing all your data independently. But with the VM, they're like much more named and like personalized. So it's not like just a ready image that you can just deploy anywhere and just destroy at will. As opposed to containers, but you can just like run from an image and you can, when you're done with it, you can destroy it and it's all the same. Basically, if you run a container image multiple times, you're gonna get the same container.
Yeah. Oh yeah, I guess it's worth mentioning. Was it in the slides? I just skipped over it. Yeah. So basically, the way you use a container is you have to like mount volumes. So
It's afterwards.
okay, afterwards. Okay. How does it work? Okay. Yes, it has layers like Shrek. Oh yeah. So this is how you build an image. So basically, an image is like you like assemble the different parts of the like container like piece by piece. So I don't really know how you explain this without a Docker file. It's like easier to step through it step by step. But basically, like you have like this specification called a Docker file in which you like specify like each thing that you will do in the container. And you can basically make checkpoints like as you go through building container. Like you might say like, oh, I want to install this package, and then I want to run this build script, and then I want to do this other thing, right? And it can basically the Docker build system will like cache like checkpoints in your container. So like if you change something in your Docker file, like it will start from like most recent checkpoint. Like so if you change like line 3, for example, like it'll start at like a cached version from line 3 and like keep going. And yeah, it is. And yeah, it saves you like computation and network bandwidth. So you don't have to like download like the entirety of Ubuntu like multiple times whenever you want to rebuild your container. Oh yes, and I guess you can consider this like an inheritance thing. So like let's say you like to use Ubuntu a lot, right? So whenever you're building Docker containers, instead of having to like re-download Ubuntu every single time, it'll just use like the cached Ubuntu image like in your on your machine if you want to like make a new Ubuntu container. So yeah, I guess that's the big idea here. Okay. So basically, it's kind of like if anyone's here is taking like 61B, it's like if a container, like the container to image thing is like an image is like a class, and then like a container is like an object, right? So it's like you instantiate the see you can have like an image, right? And you can create like 5 different containers that are like each an instance of that image, right? So yeah, and yeah, then an image is powered off. So you can like list the images on your machine, and those won't be running processes. And then you can also list containers on your machine, which will actually be like running image instances. So let's say you have like a thing called like my app, right? And you want to like bundle it. Like so you would run like Docker build like in your like project directory, and that would spit out an image. And Docker would store that locally on the machine. So it could be like Docker image ls, and you would see that image. And then if you want to run the image, then you do Docker run that image name, and then it would give you a running process, which is a container or collection of processes. Yeah, and here are the different commands. You might notice some similarities to a systemd because it is a little bit like that. Docker itself is a daemon. So yeah, you can list images, you can show running images, but yeah, I've never actually used Docker. Oh, I have. Then Docker logs. You can like okay, so that will just like list like the last n lines of container output, and you can stop, restart, and stop containers, which are just collections of processes. Right. And then these last 3 work on containers, not images, because again, a container is a running instance. If you were to run this on an image, it wouldn't give you anything because the instance is like a static collection of files. So yeah, like yeah.
Yeah. So some more commands for Docker. we got Docker build here, which is a really helpful tool. When you create your Docker file, you can build it into an image, and then you can name it with a name, and a tag. So you'll see this later on, but like almost all images that you're going to use are have a name with them, and you can either like use other people's images or use your own images later on, and it gives a really handy way to sort of reference what image you're trying to pull from. And then Docker history will just show all the commands used to make up this image. There's a lot of other tools around the ecosystem that show you like all the different layers. You can like deep dive in and see what's taking up space and like what's creating the longer build times for your image, try to optimize them. But Docker history is just a basic view of like all the different commands that people use that were used to make up the image. And then we got Docker run and Docker exec. So Docker run actually runs the image. So it'll create a container for you. It'll start it and it'll return the name. So you're able to use it. There's an option which is -IT or TI, which allows you to get an interactive shell in the container. So by default, when you run it, it'll just run in the background and the container will be doing everything without any interaction. But you can add the TI option and you get a shell into your container. So you can start typing commands, for example, if you have some special thing that you want to run inside your container. And then as Michael sort of touched on before, you can use -v for adding volumes. So this is really helpful, say if you have a database as a Docker image and you want to run your database and start making connections and adding data to your database, you want to be able to save this data because otherwise once the container stops, all the files get destroyed. And so volumes allow you to have like a persistent directory, for example, like your /data directory. You want to persist that onto your host machine so that the data doesn't get destroyed once you shut down your database. And then P allows you to add port mappings. So if you start create like an HTTP server off a Docker image, you can use that so you can access it from the internet or from your local machine. And then Docker exec is similar to the -TI. You're able to run a command inside a running container. So if you start a container normally without using TI, you can use exec later to sort of get back into that container, do any debugging you need to do, that sort of thing. And then, as I mentioned before, Docker tag allows you to create a special version of a container, of an image, sorry. So by default, when you run Docker build, it'll automatically generate like a little hash of your image. But you can create like a friendly user-facing tag so people know what they're pulling when they pull your image. So for example, there's an Ubuntu image and you can get Ubuntu 16 or 17 or 18 or 19, and your user will be able to tell based on that tag, as opposed to writing down this stupid hash. And you can also update your tags later on. So if you push a security update to your image, they can still use that same like Ubuntu 18 tag and they'll get that newer image, as opposed to these people who will be stuck on this older image, which might have the security vulnerability. And then Docker login allows you to log into a remote repository, so you can push stuff to the Docker registry so other people across the internet can download them. And then Docker push allows you to push it, as I just mentioned. So we talked a lot about like using Docker. Now let's actually dive into a Docker file and what that looks like. So all Docker files are based off of an image, a source image. So this one will start from the node image as version 18, that's the tag. And so all your Docker files will be based off a source image. And so it inherits all the stuff that the source image has done, and then you can build on top of it. Workdir sets the current directory, so similar to CD in Linux. And so you can use relative paths from now on. It'll assume it's that /app. Copy command sort of copies all the files from your local directory to the image. You can use run to run a command. So we want to run npm install. We want to install all our dependencies that we just copied into the container. And then we could use command, which is the command that we run when you do Docker run. It'll execute this command right here. So we want to do node, and then we want to start our index.js file. And then lastly, expose is just a user hint so that the users who are running your image know that it accepts traffic on port 3000. And so they can add port 3000 when they're doing Docker run. So this is more of like an advanced feature. It's not really going to be tested on any of the labs here. But you can add multi-stage builds. So if you, for example, you copy a bunch of your dependencies over and you just want to build one executable at the end, when you copy all those dependencies over, your Docker file is going to, your Docker image is going to increase in size because you're copying all those layers, and that's going to add more size to your image. But if you use a multi-stage build, you can create like a separate from statement later on and just copy your final destination, whatever you compiled. Maybe it's a special image you made or your binary, and that'll drastically reduce the size of your Docker image because it's only containing that single binary and not all the other stuff you used to build it. And now as we get sort of into the more advanced topics of it, what if I want to run multiple containers at a time? What if my system shuts down and I got to start everything back up again? There's Docker run is using Docker run itself, always an option, but that's sort of where container orchestration systems come in. So if you heard of Kubernetes or Docker Compose before or Docker Swarm, that's sort of what they do. So you can use a declarative setup to sort of write out what you want your containers to look like, what ports you want, what volumes you want, what their name should be, and Kubernetes or Docker Compose will sort of manage all that complexity for you, and keep it all running in the background as you like. As I started to mention, reproducibility allows greater networking between containers. There's a lot of commands when you're running Docker run to like create Docker networks and attach them to the containers. But these services make it much easier. And then you can also dynamically spread it across multiple hosts. So for Kubernetes, if you have like 10 different servers, you can spread your containers across all those 10 different servers automatically based on the load, as well as having to do it manually. So this is an example of how to use Docker Compose. So each of these services is a single container. So we have our database service here. We reference the Docker image that we want to use. As I mentioned before, we can add the volume. So we're going to try to persist our Postgres data in this DB data volume, which we define down here. And then we can either use a Docker manage volume. So Docker will itself allocate a space in your file system to store this DB data, and it sort of manages that, and you have no direct control over it, which allows you to take this Docker Compose file anywhere in your system and run Docker Compose up, and it'll automatically reference the same data no matter where you run it on your system. But you can also do a relative volume mount. So if you have postgres.conf in your current directory along with your Docker Compose definition, then it'll use that file and mount it directly into the container. So really just a matter of preference of which one you want to use, depending on your requirements. And then you can also define environment variables. So Postgres password, you can define the password for Postgres. So when you connect to it, you know what credentials to use. For the web container, this is kind of similar to the Postgres one, except this one will be building a Docker image. So this also, it sort of handles all this for you. So you can run Docker Compose, you can start Docker Compose, and it'll automatically do Docker build, Docker run, and also, run your special command if you have anything to override your Docker image that we defined earlier. In our Docker file, we define this command thing right here, which will be run on the container start, but you can override this at container start time if you want to run something else instead. And so that's what that option allows you to do. And then, as I mentioned before, you can set the ports. So this is a port mapping. This is from your local machine into the container. So it says, listen, any request to port 3000 on my local machine should be forwarded to the container at port 3000. And then lastly, it depends on, we can set the web container to depend on the database container. So it'll wait to create and start the web container until after the database container has been started. So now these are the commands on how to use Docker Compose. So I mentioned before, Docker Compose up will sort of will create all the containers we just defined in that file, as well as adding the volumes. We can add, by default, it'll be interactive. So you can interact with all the output of your containers and see the logs. You can use -D to sort of detach it and let it run in the background. So you get your shell back while all the containers are running. You can also do Docker Compose up service name. So you can start up an individual service. If you want to database, if you want to run maintenance on your database, for example, without starting a web application, you can run Docker Compose up DB, and that'll only bring up the database. You can do Docker Compose start to stop and start all your containers, and the Docker Compose down will stop and remove all your containers. So if you don't have a volume mounted in there, it'll destroy your data in that container. And then there are just some more commands. Docker Compose PS is pretty similar to Docker PS. So you can just see all your containers inside the project. Docker Compose logs, like to see all the logs. You can filter by a specific service. And then by default, when you run Docker Compose up, it'll check for docker-compose.yaml in your current directory, but you can also specify another file if you want to run off a different file. And then how does it apply to the OCF? So we use Kubernetes here to run all of our infrastructure. And so all of our applications run off Kubernetes, and they have all these their own containers. So OCF Web is a great example because we have three different types of containers. We have a web container, a web image, sorry, we have a web image, we have a static image, and we have a worker image. And so Kubernetes knows to run three of each of those different types. So we have 3 containers for web, 3 containers for static, and 3 containers for worker. And Kubernetes will spread them across the different servers or nodes in Kubernetes parlance. So you can see on Riptide, there's a few of the containers running, and on Bedbugs, a few containers running. And we're not defining any of that. Kubernetes is sort of managing on its own, moving stuff around as it needs to sort of make sure that all systems are running operationally. Yeah, and then Kubernetes, they call it a pod. But for our purposes of the OCF, each pod is only corresponding to 1 container, but you can run multiple containers in a pod theoretically if you want to. But I think we have a lab later on in the semester about Kubernetes, so we'll like dive more deeper into that. If that's something you're interested in. But yeah, that's pretty much it. Does anyone have any questions about containers? I know we know they're kind of fast, but yeah.
Where are you gonna put that Docker compose file?
Yeah, that's a great question. You can honestly put it anywhere you want. I know like a lot of projects will have it like at the root of the project. Like if you go on GitHub and you search like a popular thing you can run yourself, they'll have docker compose.yaml at the root of your project along with a Docker file. So typically you'll keep them together so you can run I'll go back to our Docker compose. You can see the build here and then the dot. That sort of implies it's like a ./Docker file. So it's assumed the Docker file is in the same directory as your Docker compose.yaml. But if you're not building a Docker file, you can kind of just put it anywhere that you want.
Yeah, usually like, okay, so you could have like this where it's like, I think the most common you'll see is like, you'll see like a Docker file and like a Docker compose. You can also see like for more complex projects, they might have like a mono repo where they have like many like subdirectories with Docker files in those. And then at the very project root, they'll have like a Docker compose.yaml. So it's really up to the author. Like,
But like you have the password written in this file.
oh
Yeah.
no.
Well, for this one we do.
Oh yeah. Okay.
That's not the best password. That's not the best practice. You can extract them to another separate file that you wouldn't check into like Git or something like that or version control. I think you add like a .env file, so that'll keep your password secure and like not checked into Git. But this is just for example. Oops.